Okay, guys, just like to ask you, mm, you know our previous lesson videos, right? You can watch directly from the Teams, right, without any problem.
Yeah.
Do you watch via Teams or you go to the Times and you download it? You
Usually
watch
watch team.
Teams,
Usually.
usually Teams, Okay. You can watch the old videos, the one in the first semester. You can watch,
Um, wait, let me try.
I
you
think
know,
the
yeah.
one I think the one in Teams are just the recent one. The older one, I think you have to go to the Times to access the recording.
Okay.
Okay, the Teams. Do they the Teams in Teams? Do they deleted the first semester recording of?
I'm not sure. I don't know where they store it, but inside the chat there's like the
Yeah,
recent
there is a
one.
box, right?
You cannot
Okay,
find
okay.
the previous one.
You only can find for the this week one, right? The last week one you can't find, right?
I never tried it before.
Okay, okay, okay. Just checking. Okay. Yeah, so let's be continue with our lesson today. We continue with the sorry. Okay, so we spend another 1 hour for this topic. Then we do questions, We're almost done with this topic. Okay, so just a small short recap. So we talk about electromagnetic induction. It's generator. You apply magnetic field, you apply force, you get current. Actually, you get EMF first, then you get current if it's a closed loop. First, we talk about magnetic flux. What is magnetic flux? It's the product of magnetic field strength normal to the surface area and the surface area. Okay, B dot A. Next, magnetic flux linkage multiplied by the number of turns, you get magnetic flux linkage. Then we talk about two laws, Faraday's law and Lenz's law, governing the how to get a big EMF and which direction the current will flow, or the direction of the EMF, which causes the current to flow. We concluded by using Faraday's law and Lenz's law. Okay, so how to get a big induced EMF? Longer bar, stronger field, faster swipe. A longer bar increase the area, a stronger field increase the magnetic field strength, a faster swipe decrease the time for the changes of magnetic flux linkage. So it increases the EMF. Okay. Then we talk about the graphs. If they give a flux graph, how do you plot the EMF and what do you call? If they give flux graph, how do you plot the EMF? I think these two graphs we haven't done yet, right? We haven't done yet. Okay, so let's go through here first. Okay, so hope you have tried. So EMF is what? Negative of magnetic changes in flux over time. To sketch the graph, you need to include the negative. You don't what do you call ignore the negative when you plotting graph. Okay, when you calculate the magnitude of EMF, we ignore the negative. So plotting graph, you need to consider negative. Okay, I put a d psi over dt better for me. So EMF is negative d. Magnetic flux linkage is what? BAN, BAN dt. So I told you the B inside B is proportional to what? The current flow in the what do you call in the electromagnet. So what graph is always the same? Flux, magnetic field, current. The graph is always same shape, same pattern. Pattern will be the same pattern. If sign means all three signs. EMF, you treat the flux as the velocity. Your EMF, like as I said, acceleration equals to dv dt. So you can analog to that, right? The flux, you take it as the velocity. The EMF, take it as like the analog to the EMF. So you can find the acceleration graph, flip in y x-axis, you get the EMF graph. Okay, so now this is a primary coil of a transformer. A transformer is as a, you will be learning this in AC later. A transformer made of two coils, right? It has two coils, primary and secondary. Okay. Uh, EMF EMF only works based on AC or DC. Anyone? Transformer works based on AC or DC?
AC.
AC. Yeah, Marwan? AC.
Yeah.
AC. Can it work based on DC?
No.
No. Okay, why it can't work based on DC?
It needs how do I say that? AC
Yeah.
produces what is AC produces the magnetic field inside the transformer.
Okay. So when AC current flows in the primary coil, it produces a
Magnetic flux.
changing magnetic field. Changing magnetic field. Keyword is the changing. Changing magnetic field in where? In the
Transformer.
iron core.
The iron, yes.
The iron core. In the iron core. The iron core tend to become magnet. The AC current flow in the primary coil produces a changing magnetic field in the iron core. Okay. Then what happened? The changing magnetic field will causes a changes in magnetic flux in the secondary coil. The secondary coil will experience changes in magnetic flux due to change in magnetic field in the iron core. Because BAN1, when B change, flux changing. When flux changing, you got EMF. So the secondary coil experience changes in magnetic flux. So according to what law you got EMF? According to what law you got EMF? According to Faraday's law, the changes in magnetic flux causes an EMF induced in the secondary coil. So you get a voltage here. You get a voltage in the secondary coil. So transformer works based on AC. Why transformer can't work on DC? Anybody?
Because it's only one direction, so there is not gonna be a flux change.
Very
Constant.
good. Why there? Very good. There won't be a flux change in where? In the secondary coil. Why there
Yes.
is no flux in the secondary coil? Because the iron core magnetic field is changing or constant?
Constant.
Constant. So you won't get EMF induced in the secondary coil. Okay, so the primary current flows in the transformer was shown here. It's a sinusoid. How the flux change in the secondary coil will look like? What shape? So because IB flux same shape, so current sign means flux also will be sine. Will be a sine graph. So this also sine. It will be a sine. This also sine. EMF going to be what shape? Anyone? Anybody? EMF going to be what shape? EMF is negative of rate of changes of flux. Differentiation lah, right? So the flux found to be a sine. If flux sine, you differentiate flux, you differentiate sine. You differentiate sine, what do you get? Sine
Same.
differentiate, you get what? Cos or negative cos?
Of course.
Cos. Sine you differentiate, you get cos. Okay, cos. But you have a negative, then what happened? Reflect at x-axis, so it become what graph? Become what graph? Cos. Negative cos.
Negative.
So it become negative cos. Okay, become negative cos. Okay, so the answer for EMF is a negative cos graph. Sine, negative cos graph. Okay. Okay, can you answer the question part 3? What is the phase difference? What is the phase difference between the IP in the primary coil and the EMF induced in the secondary coil?
1/4 pi.
Is it IP is what graph? Sine.
Our EMF and
Negative cos. Sine, negative cos. What is the phase difference? Your wave knowledge. You draw the cos, negative cos here. What is the phase difference? Big to big, right? Or this, right? This is your phase difference, right? This also can consider as a phase difference. How much?
Oh, okay.
How many radian? Or how many degrees?
0.5 radian.
0.5 radian. 0.5 radian?
Wait, is it?
Yeah,
Yeah.
0.5. 0.5 pi, right? Pi over 2 lah. 90 degrees, right?
Yes.
Phase is going to be 90 degrees. Or can say what? Pi over 2 radian. Okay. So here the phase difference will be pi over 2 radian, or can say 90 degrees. That's the phase difference. Okay, so this is the first part. Current graph given, flux, current and flux is the same because current affects the B affects the flux. So flux is going to change the same pattern as current. Flux and EMF, rate of changes of flux is your EMF. So you need to differentiate the flux graph and negative because negative x-axis. Yeah, any question? No questions. Okay, we go to the next one. Okay, this is also the same thing. A current carrying solenoid is placed in the near surge coil. The variation with time t of the current I in the solenoid is shown in the figure 2. The solenoid current change like this. How the magnetic field in the solenoid will change. How the EMF induced in the secondary coil will change. I is what graph? Cos graph. Magnetic field will be what graph? Anybody? Graph. So current change cos, V will change cos also, right? Magnetic field also change in a cos pattern. It's the same pattern. Sorry, go down. Same pattern as the above law. This is also going to be cos. Okay, come on, predict for me EMF going to be what graph?
Negative sign.
Cos, you differentiate, you get what?
Oh, positive.
Positive. Cos, you differentiate, you got negative sign. Then you reflect some more, right? So it become positive sign. Okay, yeah. It's going to be a positive sign. Sorry. Okay, it's a sine graph. It's a sine. Okay, guys, so you got the answer. So current, magnetic field, flux, same shape of graph, EMF. You imagine this as your velocity, differentiate the velocity, you get the acceleration. Acceleration can analog to EMF up to you become negative, it reflect in x-axis. That's your EMF graph. Okay. Okay, let's go one pass here about this. This is important. Just about plotting the graph. One pass here. Oops, where's the first question? Missing. Okay, let me check. Oops. Guys, hold on. Yeah, okay. Oh, this we done. This one. Okay. Okay. So this is one question. Page, I think page 17, you can see the question. It's Juno 5. Okay, state Faraday's law, you know that. We go to the 2. So the magnetic flux change like this. How's the EMF graph going to look like? Okay, come on, sketch. 1 minute for you. What must be in your mind? EMF equals to negative d psi over dt. Please consider the negative when you plotting graph. Okay, use this. Flux is BAN. The B is found to be proportional to I. This is the story. If your B is like this graph, how's your EMF graph going to look like? Guys, can you take a snapshot, draw and snapshot, send me to the WhatsApp? Let me see. Sketch the graph. Just send me WhatsApp. Okay, all of you still doing, yeah? Come on. Just take a picture and send me. Okay, I got one. Shike, I think you have to draw the last one, 3T to above. Yeah, that's fine, good. 3T above, you should draw. Okay. Okay, class. Okay. So 2 of you send me. Okay, one correct, one got problem. You see, if you have struggled to visualize how to plot this graph, as I said, the B is same as your flux, right? But I imaginary, I ask you to imagine like what? Imagine this like your velocity graph. This is your velocity graph. Imagine your velocity graph. You draw the acceleration graph here. EMF is like the acceleration graph. Okay, sketch that first. This is your velocity graph. Draw the acceleration graph. How does it look like? Then you make reflection of x-axis. You'll get the graph. Okay. So if this is the velocity graph, getting more. Okay, good. Gavin, good. Yeah, Marwan. Okay, good. Some of you got it there. So you take it as a velocity graph. So velocity graph, this velocity constant. So acceleration will be what? 0 lah, right? 0. Then this velocity is gradient is acceleration. Gradient is positive. So what happened? The acceleration graph going to be up here, positive, constant. Okay. Then here the velocity is decreasing but constantly, but negative gradient.
I would say it's negative, right?
Yeah. First we draw the VT graph first, acceleration graph first, It'll be like this. Then finally 0. Okay, this is how your acceleration graph should predict it. But because we want EMF, you must reflect at x-axis. So the actual graph going to be what? 0, 0. The negative going to be, the positive going to become negative down here. Graph going to change like this. And the negative going to become positive. Okay. And 0. Yeah. So finally, a graph should be like this. Correct? Okay. So yeah, this is my point of view. If you have struggled to view the flux with the EMF, just predict as velocity and acceleration. But don't done with acceleration. Once you draw acceleration graph, don't think that's your EMF. You have to reflect at x-axis. Okay. Okay, good. So that's about plotting graph. Plotting graph. Okay, next, let me go further. Okay. Before we go to this, before we go to this, I just want to show you something, because I think last week we had a problem with discussing when the magnet is dropped into a solenoid, how the graph going to change. Okay, see, this is one animation here. Okay, so here the magnet is dropped through a solenoid, but the solenoid is quite a short tunnel. The size of the solenoid is comparable with the magnet. This is the EMF going to change. Okay, but this is not our focus. Our focus is the next one. The solenoid is a big tunnel, a longer one. Magnet is quite small. When it dropped inside, how the EMF changed? The graph will be like this. Okay, the graph will be like this. You have when the magnet enters the what do you call the tunnel completely, the EMF will become maximum and 0 again. Once the B is here, B is at this point where the magnet is completely inside the tunnel already. The north is already just nice at end here, completely inside. Okay. Then after that, there is a region B to C. The magnet is completely traveling inside the tunnel. No EMF is induced. That means what? When the magnet go inside the tunnel completely moving in, flux change is 0. So no EMF induced. When it about to leave, C is about to leave. Leave means the south just emerging from the bottom. Then EMF will be induced again. But the EMF induced now is in opposite direction, because the pole going to generate is changes. Because down going to produce south now. When the magnet is going up, down was north. But when it comes down, leap north, so it becomes south. So the EMF direction will change. But the magnitude also going to be big compared to when it going in. Why? Act of gravity, right? Because moving faster. When it move faster, the rate of changes of magnetic flux is greater, so you get greater EMF. Okay. So this is what we discussed. Longer one, inside when it travel, no change in flux, no change in EMF. Okay, any questions from here? Okay, no questions. Okay. Yeah. Any questions? No questions. Okay. So we go to the last part. The last part we're going to talk about is eddy current. Okay. You see, a pendulum of magnetic field, a solid copper pendulum is solid, oscillating solid copper pendulum is brought to rest almost immediately by an electromagnetic field. This is due to the eddy current induced in the solid copper pendulum. In this pendulum, when this copper plate oscillate between the magnet, what happened? The magnet experience damping. What is meant by damping? Reduction in the energy of the oscillating system. Why it loses energy? Because the conductor generate eddy current. Okay, what is meant by eddy current? Eddy current, I need to show this. Okay. For example, I'll show this. Sorry. Okay, eddy current. So this is diagram. So you look at this diagram. There is a magnet here on top, so, electromagnet. You use an AC, okay, alternating current. So the current flow changing direction continuously. What happened? The magnetic field strength here changing. So the magnetic field strength causes a changes in magnetic flux on the conductor. Okay. So when the bottom of this electromagnet induces north, the conductor on top will try to induce what pole? Will try to induce north, because you want to oppose the change, right? Lenz's law. So you have a conductor like this, and you want to create a north on top. How the current should flow in this conductor? Like a right-hand grip rule, you know, a right-hand grip rule. How the current should flow? Current should flow clockwise or anti-clockwise to produce a north pole on top. So look at from the top your finger. It should be clockwise, anti-clockwise.
Anti.
Should be anti-clockwise. So the current here should flow anti-clockwise. Okay. So what happened? A circulating current will appear on the conductor just for the sake of producing north pole on top. According to Lenz's law, you oppose the change. Okay. So this type of current, which moving in a circular path, is called eddy current. This is called eddy current. Okay. Eddy. The term eddy means circulating current used in liquid. Eddy current, like a circulating movement. So this is called eddy current, move in a circular path. Okay, all electron going to move in a circular path like a drunken electron. Okay, generate the north pole. This type of current going to give heating effect to the material, because current is flowing, heat will generate. Heat will be generated. So the heat up the body. It will heat up the body, and might slows down any movement. For example, just now you see you have a conductor, a copper in a shape like this, and it's oscillating. And you apply a magnetic field this way. When you apply a magnetic field this way, what happens? Eddy current will form in the copper. Circulating current will form in the copper. So what happens? Heat will be generated in the copper. So the heat energy actually retrieve from the oscillating energy of the copper. Okay, so the oscillation will experience damping. Okay, so that's why eddy current means normally closely linked to heat, and heat will reduce the efficiency of the system. Okay, that's what's stated here. Eddy current are closed loop of induced current circulating in a plane of perpendicular to the magnetic flux. They normally travel parallel to the coil winding, and the flow of limited to the area of inducing magnetic field. Move in a circle. The eddy current generates thermal energy and reduces the efficiency of the system. If it's a moving system, you can use eddy current like a braking system, brake, slow down by removing energy from the system. Okay, any questions? So this is the introduction of eddy current. Okay. So now, this is the eddy current. When the copper move back and forth, what happened? Eddy current forms in this copper and generated heat. So now, how do you avoid it slowing down? How do you minimize eddy current? How you can minimize eddy current here? So they minimize the eddy current by using something called perforated copper pendulum. Perforated means like with lots of holes, got lots of holes. like or got some sort of insulator in between, have an insulator in between. Okay, insulator, like a insulator thing, or you have something like, sorry, this, perforated means like you have something like this, and you have kind of a insulator in between, or you have something like what do you call? You have a holes here and there, holes. Okay, so this is called perforated. How perforated can minimize eddy current? Anybody? How perforated, by having an insulator in between conductor, how we can minimize the eddy current? Anybody? Because how eddy current moves? Eddy current moves in a circle. Okay, if the surface area is very huge, the circle going to happen, a big circle, a lot of electron going to move around, big circle. Okay, but if you put what do you call insulator, if you put insulator in between, okay, the big circle won't happen. Why it won't happen? Electron cannot pass the insulator. So now how the eddy current going to flow? Eddy current only make a small circle. It's just a small circle. It cannot make a big circle. He's stuck because it cannot pass the insulator. So make a small circle. So that means, do you have eddy current? Yes, you still have eddy current, but the eddy current has been minimized by make the electron move in a smaller circle. Okay, so eddy current can be minimized by using a perforated copper pendulum. This one wheel. Okay, so yeah, so this diagram, if the copper pendulum is perforated, it is not brought to rest immediately by the electromagnetic field, indicating that the eddy current is not produced in this, not to say not produced, minimized eddy current. Okay, a small eddy current, very limited eddy current is produced. So the braking effect is not that significant. Okay. Okay. Do you remember transformer? Okay. I don't know whether you still remember or not. When you learn your Form 5 O levels and SPM, the transformer, you have a coil here. Okay. You have a coil here. The transformer has some efficiency. The efficiency of a transformer is dropped by because some energy is lost to many ways. Transformer loses energy in 4 ways. I don't want to discuss all the 4 ways now. One of the way is due to what? Due to eddy current. If you remember in your Form 5 studies last time, eddy current is one of the reason. There are 4 reasons how it loses energy, but one of the source is eddy current. You still remember? Eddy current causes the efficiency of transformer drops. Okay, where the eddy current happens in the transformer is in the iron core, the big block of iron core. When current start to flow, what happened? Circulating current appears in the core. Eddy current forms. Okay, because changing magnetic field happen, so eddy current will form to oppose it. This eddy current causes heating effect to the transformer, reduces the efficiency. Okay, can you tell how they minimize this? Anyone?
Making the core layer.
What they did? They did the
A layer in between the core.
we call it what? Laminated.
Laminated.
Laminated iron core is used. Laminated iron core is used. What is laminated? I think the core is made of small slices of iron. Few slices of iron combined together, it formed the block. Every iron in between they put an insulator. There is an insulator in between. So the eddy current can't make a big round. It only can make a small rounds. So eddy current is minimized. So efficiency is increased. Okay. This is eddy current. So what is meant by eddy current? Anybody? Conclusion. What is eddy current? A type of current formed in a block of a conductor in a block of conductor due to changes in magnetic field. Due to changes in magnetic field, a block of conductor. Eddy current, good or bad? Normally bad, but we can use it for a braking system. Okay. Okay. Yeah. So eddy current move in a circular path. How do you minimize eddy current? By using a laminated iron core in the transformer or perforated block might minimize the eddy current. Okay. Any questions, guys, from here about eddy current? Okay, let me show you one video. Okay, to understand about eddy current. Interesting video. Okay, this is one demonstration actually. See the demonstration. Iron, and okay, this is called eddy current. You have lots of videos in it. Okay, so just now you see, yeah. Okay. Okay. Sorry. Let me. Okay. Okay. Sorry. Okay. I just want to pause it. Okay. You see this diagram here. The magnet is falling down. The down here may be North Pole. When it goes down, what happened? You can see the magnet is slowing down like a slow motion. And it never really make a big impact. It slows down like a cushion. What happened here? Eddy current is formed here in this copper in a circulating current. We generate a North Pole on top. So the magnetic field, like a force upwards, is exerted. So it slows down. That's what happened. So eddy current forms where? Eddy current forms in the block of conductor in this copper. You get the eddy current. Okay. Yeah. Any questions? So this is one example. You can see lots of videos from there. Okay.
So isn't the current also also is technically current generated by magnetic field, but
Yeah, in a wire, yes.
So it's just unuseful electric current.
Very good, yes. We cannot retrieve the eddy current. Okay. If we can use the eddy current to generate a light bulb, it's a very good thing, but we don't know how to retrieve it because it moves in a circle within the conductor. So very difficult to retrieve it. So that's called eddy current. Eddy current means a type of current which moves in a circular path by itself. Yeah. Okay.
Or like if we laminate transformers, for example, then reduce eddy current, but wouldn't it also reduce a little bit of the efficiency of it converting towards the second solenoid?
Yeah, definitely. Yes, definitely. Yeah. That you will learn in depth if you go for electrical engineering later.
Okay.
Okay. The eddy current how eddy current affects the current generated in the secondary coil. There is one story behind it. But for time being, we never discuss about that. Okay. Okay, guys. So that's all about this topic. Okay, this topic finally what you learn is about eddy current. Then that's it. Okay. So what is the application of electromagnetic induction to us? Definitely, induction plays a very important role in our daily life. First is of course the generator. Without generator, no electricity. Okay, you can have radioactive substance, you can have a nuclear reactor, you can have a hydroelectric dam, but if you don't have a generator, you can't change the energy to electricity. So of course, generator is first application. Second, definitely transformer. Transformer is another application of induction. No transformer means what's the problem you're going to face? A world without transformer. What's the problem you're going to face? The voltage cannot be altered. You can't charge your phone. The TNB gives us 230 volt. 230 volt. If you don't have transformer, you cannot bring down the voltage to, what is the charging voltage of a phone? Maybe around 6 volt, 9 volt, 6 volt, I think. So without transformer, you can't charge your phone, you can't on your television and so on, because different material, different device is using a different voltage. So transformer. Okay. Yeah. So that's about it. Okay. You have lots of questions at the back. You can give a try. Okay. So we go back. We just try one question. Okay. Okay. Normally, this EM induction will be together with AC, alternating current. Alternating current is the next topic we're going to discuss. Okay. What link the induction together alternating current is the transformer. The transformer link the alternating current and induction as a one team. When we talk about transformer, we have to talk about AC and induction. Yeah. That's why they are together will be one question in exam. Okay. Okay, let's go for first question. First question. Transformer was given, soft iron. Scroll down. The current flow in the primary coil is found to be like this. Okay, now, can you sketch how the EMF induced in the secondary graph going to look like? Okay, 1 minute for you. This is your primary current. How the EMF in the secondary current going to induce? Draw the graph. EMF is negative of the rate of changes of magnetic flux linkage. Okay, imagine if you have a struggle to sketch the graph, the current graph, or the flux graph, take it as a velocity graph. You sketch the acceleration and reflect at x-axis, you get the EMF graph. Okay, spend 1 minute. Okay. So first, no current, like velocity 0, acceleration will be 0. Like velocity graph going like this. If your VT graph like this, or say AT graph looks like. VT graph like this. Greater acceleration becomes 0, right? but positive. So the graph going to be up to down, right? This is your AT graph going to looks like for the second one. So, but here we have to draw what? It's a reflection of x-axis. So this graph, we reflect x-axis is going to be like this, right? So here going to be like this. Okay. Second one. Third one, velocity constant, acceleration like 0 lah. No flux change, no EMF. Okay. That one. Fourth one, like flux dropping or VT dropping. Why I'm saying flux? Current, magnetic field, flux, same shape. Okay, so flux is dropping. So VT graph, imagine like a VT graph. VT graph going like this. How's the acceleration graph looks like? It's going to be constant but negative, right? Negative. But here we reflect at x-axis, it becomes positive. So you go up, positive. Like flat line. Sorry, straight line. Like a box. Like a box, sorry. Box and go 0. Okay, so this is the shape of the graph. EMF is rate of changes of magnetic flux. Okay. Any questions, guys? So this is your transformer. Okay. So you have many questions here, and why not do as a homework? Okay. We spend another maybe about half an hour next class to discussing these questions. Okay, we'll be discussing these questions. Today, please give a try this paper. Look at the question, check the answer. So tomorrow I'll ask you if you have any questions. If you don't have, I select randomly and we discuss. Okay, we do randomly and discuss. Any questions, guys, from here? So do this all as an homework. Do it as a homework. This question, some are mixed with AC. So like AC questions you don't do. The magnet one, you give a try. Okay, give a try. Okay. So today I stop here. Any questions? No questions. Okay, so tomorrow we'll be doing this question. You give a try. If you don't have any questions, we discuss. After that, we're going to start with alternating current. Next topic. Okay, AC, which is quite close linked with induction. Okay. Okay, guys. So I see you tomorrow.